Good day, everyone. In this presentation, we will discuss the advantages and disadvantages, types, construction methods, design considerations, load transfer mechanisms, and load bearing capacity of drilled shaft foundation. In civil engineering, the foundation is one of the most important components of any structure, as it safely transfers load to the ground. When the surface soil is not strong enough to support these loads, engineers use deep foundation systems. One of the most widely used deep foundation is a drilled shaft foundation, also known as caissons, piers, or drilled piers. Drilled shafts are constructed by excavating a hole into a ground and filling it with concrete, and often with reinforcement. These foundations are typically 750 mm or more in diameter and are commonly used in bridges, buildings, and heavy structures, especially in areas with weak or variable soil conditions. Sometimes, casing is installed to prevent soil collapse during excavation. These shafts provide support through end bearing and side friction, depending on soil conditions. Drilled shafts offer several advantages. A single shaft can replace multiple piles, reducing construction complexity. They are easier to construct in dense sand and gravel. They produce minimal vibration, making them safe in near existing structures. They are quiet since no hammering is required. They provide high resistance to lateral loads. They also allow visual inspection, ensuring quality control. They are also economical, especially in poor soil conditions. However, there are also limitations. Construction may be affected by weather conditions, especially during concrete placement. There is a risk of ground loss or soil collapse during deep excavation. Improper handling may affect nearby structures. There are three types of drilled shafts: the straight shaft, bell shaft, and socketed shaft. A straight type extends through weak soil and rests on a strong layer. Load is carried through end bearing and side friction. Also, it may be cased with a steel shell for stability. A socket type extends into rough layers for added stability. Load is resisted through end bearing and shear along the rough interface. Drilled shafts are commonly constructed using rotary drilling in the US. There are three main methods based on soil conditions: the dry method, casing method, and wet method. Dry method used for stable soil above the water table. Case used for unstable soil that may cave in. Wet method used for water saturated soil and deep excavations. Dry method used when rock does not cave in after drilling. Steps in dry method. Step 1 is the start of drilling, where a hole is excavated using proper equipment. If needed, the base is widened to increase strength. The removed soil called spoils is placed nearby. This step prepares the hole for the foundation. Step 2 is a start of concrete pouring, where concrete is placed into the drilled hole. This fills the cylindrical shaft and begins forming the foundation structure. Step 3 is the placing of the rebar cage. If required, steel reinforcement is inserted into the upper portion of the shaft. This helps strengthen the foundation and allow it to resist tension and bending forces. Then step 4 is the completion of the drilled shaft. After the concrete has been fully poured and set, the drilled shaft is completed. At this point, we will show a video demonstration of the completed drilled shaft. Encasing method, commonly used in soil or weak rock formations where there is a risk of collapse or excessive deformation during drilling or excavation. This method ensures the stability of borehole by installing the protective casing as the excavation processes. Steps in casing method. Step 1, same as the dry method, initiate drilling. Step 2, drilling with slurry. The slurry helps support the walls of the excavation by exerting pressure, preventing soil or rock from caving in. It also assists in carrying cutting to the surface. Step 3. Introducing casing. As drilling continues, a casing is inserted into a borehole. This casing provides structural supports to the sides of the hole, ensuring that it remains open and stable, especially in loose or water-bearing soils. Step 4. Cleaning and sealing. Any debris or slurry inside the casing is removed. The interior is then prepared for the next phase of construction, such as concrete pouring or installation of structural elements. Step 5. Drilling below casing. A smaller drill bit is used to continue excavation beneath the installed casing. This allows the borehole to reach deeper layers while upper portion remain protected and stable. Step 6. Under reaming. In this stage, the base of the borehole is enlarged to create a wide foundation. Step 7. Removing casing. After reaching the desired depth and completing the necessary excavation, the casing is gradually withdrawn. This step is carefully controlled to ensure that the surrounding soil remains stable during removal. And step 8. Completed shaft. The excavation is finalized. Concrete is then poured into the borehole. The wet method, also known as the slurry displacement method, is used to maintain the stability of a borehole during excavation by filling it with slurry. These techniques prevent the collapse of soil by exerting pressure along the borehole walls. The process begins with drilling to full depth, where excavation is carried out while continuously filling the hole with slurry to support the surrounding soil. Once the required depth is achieved, reinforcement is placed into a borehole. If structural support is needed, concrete is poured into a borehole. The concrete displaces the slurry as it rises, ensuring that the borehole is filled from the bottom up without contamination. Finally, a completed shaft is formed once the concrete fully replaces the slurry and sets, resulting in a stable and structurally sound foundation. In this slide, the figure shows key elements of drilled shaft construction. The auger, a rotating tool used to drill and remove soil creating the borehole. The reinforcement cage, a steel framework placed inside the hole to provide strength and structural support. The clean out bucket, used to remove loose soil and debris from the bottom, ensuring a clean base for concreting. Therefore, it is important to recognize that drilled shafts are complex foundation elements whose performance depends on several factors, including soil conditions, loading characteristics, and construction methods. Proper design ensures that the shaft can safely transfer load to the ground while maintaining structural integrity over its service life. The next slide presents other design considerations, focusing particularly on reinforcement requirements and their role in ensuring a stable and durable drilled shaft foundation. So a minimum steel ratio of 1% of the shaft's gross sectional area is recommended, particularly for normally reinforcement shafts in accordance with building codes. The design relationship is expressed as Fc equals 0.25 Fc prime equals Q sub W over A sub G, or in terms of shaft diameter, D sub S equals square root of Q sub W over pi divided by 4 times 0.25 FC prime equals 2.257 square root of Q sub W over FC prime, where D sub S is the diameter of the shaft, Q sub W the working load of the drilled shaft, A sub G is equals to gross cross-sectional area, and FC prime the concrete compressive strength. In addition, if tensile forces are anticipated, the reinforcement cage must extend throughout the full length of the shaft to ensure structural integrity. The other design consideration is the concrete mix design. The concrete used is similar to regular structural concrete, but it must meet specific requirements. First, the concrete should be flowable, meaning it can easily pass through the reinforcement. To achieve this, a recommended slump of about 15 mm is used, ensuring proper workability. Additionally, the maximum aggregates size is limited to 20 mm to allow smooth placement inside the shaft. Moreover, higher grade concrete is typically used to improve the load bearing capacity and overall performance of the foundation. To better understanding, let us consider a sample problem. A straight drilled shaft is required to carry a load of 6 meganewton and the concrete has a 28 days compressive strength of 50 meganewton per meter squared. Question A. What should be the diameter of the drilled shaft? B. If a minimum reinforcement of 1% is provided, to calculate how many 16 mm diameter reinforcing bars are needed along the perimeter. The drilled shaft is required to carry a load of 6 million newtons, and the concrete has a compressive strength of 15 million newtons per square meter. The minimum reinforcement ratio is 1%, and the diameter of the reinforcing bar is 16 mm. First, we solve the required diameter of the drilled shaft. Using the given formula and substituting the values, we compute the diameter. After solving, the required shaft diameter is 0.782 meter. For practical purposes, this is approximated to 800 mm diameter. Next, we determine the number of reinforcing bar needed using the minimum reinforcement requirement of 1% and a bar diameter of 16 mm. We apply the formula. After computation, the required number of bar is 25 bar. Therefore, the drilled shaft should have a diameter of approximately 800 mm and 25 pieces of 16 mm reinforcing bars. Now, let us discuss the load transfer mechanism in drilled shaft as shown in the figure. Shaft dimensions. The diagram shows the actual geometry or dimensions of the drilled shaft. This includes the diameter and length of the shaft, as well as the position where the load is applied. These dimensions are important because they directly affect how the load is transferred to the soil. The next is the load settlement curve. This graph shows the relationship between the applied load and the resulting settlement of the shaft. It also separates the contribution of total load, side resistance, and base resistance. From the graph, we can observe that side resistance develops earlier, meaning it reaches its capacity before the base resistance becomes fully effective. Finally, the third figure illustrates the load distribution along the depth of the shaft. It shows how the applied load is gradually transferred from the top of the shaft down to the surrounding soil layers. As depth increases, part of the load is carried by friction along the shaft, while the remaining load is transferred to the base at the bottom.
Now, we will discuss the load-bearing capacity of the drilled shaft foundations. Drilled shafts carry loads through two main mechanisms. First is the resistance at the base, and second is the friction along the shaft. These two components work together to support structural load safety. So for the ultimate load capacity formula, we have Q sub U is equals to Q sub P plus Q sub S, where Q sub U is the ultimate load, Q sub P is the ultimate load carrying capacity at the base, and Q sub S is the ultimate load carrying capacity along the shaft. So based on this figure, a drill shaft with a bell has an enlarged base that increases its contact area with the soil, allowing it to carry higher loads mainly through end bearing. It is the best used in weak upper soils and stronger layers below because it reduces settlement and provides high stability. This type is commonly used for heavy structures such as bridges, high-rise buildings, and large columns. However, for a straight drill shaft has a uniform diameter and carries load through both skin friction and end bearing. With skin friction often being significant, it is simpler and more economical to construct, making it suitable for soils with good side resistance. This type is commonly used for moderate load structures such as residential buildings, commercial buildings, and towers. Equation 13.3 expresses the ultimate base load Q sub P in a form similar to shallow foundations, while incorporating the effects of soil compressibility as introduced earlier. When applying this equation to deep foundations, the footing width B is replaced by the pile diameter D, and the effective vertical stress at the pile base is taken as Q prime is equals to gamma prime times L. For long piles, where the length L is much greater than the diameter D, the contribution of the third term involving the N sub gamma factor becomes very small compared to the second term. Since the bearing capacity factors and the correction factors are of similar magnitude, this term can be reasonably neglected without significant loss of accuracy. With this simplification, the expression for the base resistance becomes more practical, and by combining it with shaft resistance, we obtain equation 13.4. For equation 13.5, this equation gives the net ultimate base capacity Q sub P for a drilled shaft in granular soil, where cohesion is zero. Since the soil is cohesionless, the load capacity is mainly controlled by effective stress and frictional resistance. The term N sub Q minus 1 is used to represent the net effect of the bearing capacity factor. The factor N sub Q includes both the soil resistance and the existing overburden pressure, so subtracting 1 removes the initial stress that is already present in the ground. These equations define the correction factors used in the previous expression. The shape factor F sub Qs depends on the soil friction angle phi prime, indicating how shear strength affects capacity. The depth factor F sub Qd accounts for the embedment ratio L over D, showing how deeper piles increase resistance. Finally, the constant C, which is also a function of phi prime, is used in calculating the depth factor, reinforcing that friction angle plays a key role in granular soil behavior. According to Chen and Cole-Ho, to account for compressibility effects, we calculate the rigidity index of the soil. First, the critical rigidity index I sub CR is determined using table 13.1 based on the soil friction angle given. Then the reduced rigidity index I sub RR is calculated, which incorporates soil stiffness, effective stress, and other soil properties. In the next step, we compare the reduced rigidity index I sub RR with the critical value I sub CR. If the I sub RR is greater than or equal to I sub CR, the compressibility factor is equal to 1, meaning compressibility has a little effect. However, if I sub RR is smaller, use equation 13.17 to solve compressibility factor. Additionally, equation 13.18 provides an alternative approach using a modified bearing capacity factor N asterisk sub Q, which can be obtained from the table 13.2 based on the soil friction angle. It also includes a correction factor omega, which accounts for the pile geometry, especially the ratio of length to diameter L over d sub b. The variation of omega is given in table 13.3, where interpolated values are used depending on the L over d sub p ratio. This table 13.1 shows how key parameters vary with the soil friction angle phi prime. As the friction angle increases, the bearing capacity factor N sub q, shape factor F sub qs, and rigidity index values generally increase, indicating stronger and stiffer soil behavior. At the same time, some parameters like C and N decrease, reflecting changes in how compressivity and stress distribution are accounted for. Next is table 13.2. It provides values of the modified bearing capacity factor and asterisk sub q based on the soil friction angle. As the friction angle increases, N asterisk sub q increases significantly, which means higher load bearing capacity. These values are used in the simplified equation to estimate base resistance more practically. Next is the table 13.3. This table shows the correction factor omega, which depends on both the soil friction angle and the ratio of pile length to diameter L over d sub p. Generally, as the pile becomes longer relative to its diameter, the value of omega decreases. This factor adjusts the base capacity to account for pile geometry effects. The shaft resistance Q sub S represents the frictional resistance developed along the pile surface. It is calculated by integrating the unit skin friction along the entire length of the shaft, as shown in the equation 13.20. In simple terms, this means the total shaft resistance is the sum of the friction acting over the depth of the pile. Next is we describe the equation 13.23, where P is equal to shaft perimeter, F is the unit frictional or skin resistance, K is the earth pressure coefficient, and sigma prime sub O is the effective vertical stress at any depth Z. Substituting this into equation 13.20 gives equation 13.23, which shows how shaft resistance depends on soil properties and depth. Next, to obtain the allowable load, we apply a factor of safety to the ultimate load. As shown in the equation 13.24, the allowable net load is calculated by dividing the sum of base resistance and shaft resistance by the factor of safety. This ensures that the design remains safe under working conditions. Next is the load bearing capacity in granular soil on settlement. So this section introduces a method based on settlement, developed from load test data by Rees and O'Neill. Instead of only using theoretical equations, this approach relates load capacity directly to how much the pile settles. Equation 13.25 shows that the ultimate load is made up of two parts: the shaft resistance, which is the sum of friction along each layer, and the base resistance at the pile tip. This method provides a more realistic estimation because it considers actual field behavior. The figure 13.10 illustrates how load is transferred along the drill shaft. The total load is distributed between shaft resistance along the sides and base resistance at the tip. The shaft is divided into layers, and each layer contributes frictional resistance. It also shows that some zones, like near the bell or in certain soils, may not contribute to load transfer. For the equation 13.27, this equation defines the parameter beta sub 1, which is used to calculate the unit shaft resistance. It shows the beta sub 1 depends on depth, meaning the shaft resistance changes as we go deeper into the soil. For the equation 13.28, it gives the unit point resistance at the base of the pile. It shows that Q sub P is directly related to the standard penetration value, N60, which represents soil strength. So higher N sub 60 values indicate stronger soil, and higher base resistance. Next is the equation 13.29, reduction of Q sub P. This equation is used to reduce the point resistance when the base diameter is large. If the diameter exceeds a certain value, excessive settlement may occur, so the calculated base resistance is reduced. This ensures that the design remains safe and realistic. Next is the equation 13.30. This equation modifies beta sub 1 for soils containing 25 to 50% gravel. It shows that beta sub 1 depends on depth and is adjusted using empirical constants. This helps improve the accuracy of shaft resistance calculations for gravelly soils. Lastly is the equation 13.31. This equation is used when the soil contains more than 50% gravel. In this case, beta sub 1 is calculated using an exponential relationship which better represents the value of very coarse soils. This provides a more accurate estimation of shaft resistance under these conditions. Figure 13.11, normalized base load transfer versus settlement in sand. This shows how base resistance develops with settlement. As settlement increases, the base load also increases, but not linearly. The curve helps us estimate how much of the ultimate base resistance is mobilized at a given settlement. This is useful when designing for allowable settlement rather than ultimate capacity. Next is the figure 13.12, normalized side load transfer versus settlement in sand, gravelly sand, and gravel. Similar to base resistance, the side resistance increases as settlement increases. However, it reaches a maximum value and may stabilize or slightly decrease depending on soil conditions. This helps us determine how much shaft resistance is mobilized at different settlement levels. Next is the table of constants. Beta sub 7, beta sub 8, beta sub 9, and beta sub 10. This table provides the constant values used in previous equations. These constants are applied when calculating the shaft resistance for gravelly soils. They are determined from experimental data and help refine the estimation of load capacity based on soil conditions. Sample problem, example 13.2. A soil profile is shown in the figure 13.13. A point-bearing drill shaft with a bell is placed in a layer of dense sand and gravel. Determine the allowable load the drill shaft could carry. Use equation 13.5 and a factor of safety of 4. Take d sub s equals to 1 meter and d sub b is equals to 1.75 meter. For the dense sand layer, phi prime is equals to 36 degrees and E sub s is equals to 500 Pascal, and ignore the frictional resistance of the shaft, which is negligible compared to the end bearing load. So these are the given. Next is the solution. The first step is to calculate the effective vertical stress at the base of the shaft, Q prime, using the soil unit weights and the layer depth. Next, the shape factor F sub Qs, constant C, and the depth factor F sub QD are obtained, followed by the critical rigidity index and the soil modulus. Then the reduced rigidity index is calculated and compared with the critical rigidity index to determine the compressibility factor F sub QC. Since compressibility affects the base resistance, this factor is needed before solving the ultimate base capacity. After finding all the required factors, the base area and the bearing capacity factor are used in equation 13.5 to calculate the net ultimate base capacity. Once the ultimate base capacity is obtained, it is divided by the factor of safety to determine the allowable base load. From the calculations, the allowable load is about 6,629 kilonewtons. Next is example 13.3. This example solves the same drill shaft problem from example 13.2, but now using the Berzantsev method based on equation 13.8. So therefore we have the same given but different solution. The first step is again to calculate the effective vertical stress at the base of the shaft, Q prime. Next, the modified bearing capacity factor N asterisk sub Q is obtained from table 13.2 using the soil friction angle given, and the correction factor omega is determined from table 13.3 based on the ratio of L over D sub B. These values are then substituted into the equation 13.8 to calculate the net ultimate base capacity. Finally, dividing by the factor of safety gives the allowable base load, which is about 6,321 kilonewtons. This result is slightly lower than the previous method, but still provides a practical estimate of safe load capacity. For the last sample problem, problem 13.4, a drill shaft is shown in a figure 13.14. The uncorrected average standard penetration number N sub 60 within a distance of 2D sub B below the base of the shaft is about 30. Determine A, the ultimate load carrying capacity, use equation 13.30. B, the load carrying capacity for a settlement of 12 mm. So these are the given. The N sub 60 is 30. Next is the solution. So in part A, the soil is divided into layers so that the shaft resistance can be calculated more accurately. The value of beta sub 1 is determined for each layer. Then the effective vertical stress and skin friction are computed to obtain the total side resistance. Next, the point bearing capacity is calculated from the given N sub 60 value, and since the base diameter is greater than 1.27 meters, equation 13.29 is used to reduce the point resistance. Adding the reduced base resistance and the total side resistance gives the ultimate load capacity, which is about 4,030 kilonewtons. Next, in part B, the allowable settlement is converted into normalized settlement values for both the shaft and the base, using figure 13.12b for side load transfer and figure 13.11 for base load transfer. The corresponding mobilized side and base sides are obtained. Adding this gives the load capacity at 12 mm settlement, which is about 1,766 kilonewtons.
So in load-bearing capacity in clay, when dealing with saturated clays where the friction angle or phi is equals to 0, the bearing capacity factor NQ becomes equal to 1. This simplifies our bearing capacity equation. Under this condition, the net point resistance or the load carried at the base of the drilled shaft is expressed using the cohesion Cu and the modified bearing capacity factor, assuming that the shaft length L is greater than or equal to 3 times the base diameter dB. Equation 13.32 may be rewritten into a simplified form. This results in QP net is equals to AP times Cu times NC, where NC is modified bearing capacity factor that depends on the soil rigidity index. Here, where the soil rigidity index was defined in equation 13.11, the value of NC is controlled by the soil rigidity index represented as IR. From the book, for clays where phi is equals to 0, the rigidity index is defined as IR is equals to ES over 3 times Cu, where ES is equals the elastic modulus of the soil and Cu is the undrained cohesion. This index helps us relate the stiffness of the clay to its shear strength. A higher rigidity index means the soil is stiffer relative to its cohesion. For very long shafts, specifically when L over dB is less than 3, O'Neill and Rees provided a correction to estimate NC properly. Aside from the point resistance at the base, drilled shafts also develop skin resistance along their length. In clay, the skin resistance equation is very similar to that of piles. It is computed by integrating the adhesion alpha times Cu along the perimeter of the shaft. This adhesion factor alpha depends on the relationship between the soil cohesion and the atmospheric pressure. Kulhaway and Jackson performed field tests on 106 drilled shafts, 65 in uplift and 41 in compression. From these tests, they derived the best correlation for estimating the adhesion factor alpha. The correlation shows that alpha depends on the ratio of atmospheric pressure PA to cohesion Cu. To be conservative, the value of alpha is typically taken as 0.4. With this value, we can calculate the skin resistance and the point resistance to estimate total load-bearing capacity. So here in table 13.4 provides the relationship between the soil stiffness ratio ES over 3 Cu and the modified bearing capacity factor NC. This table, based on work by O'Neill and Rees, helps us select the appropriate NC value for various soil conditions. Generally, if the ratio of Cu over Pa is equal to or greater than 1, then NC can be taken as 9. In problem 13.5, figure 13.17 shows a drilled shaft without a bell. Here, L1 is equals to 12.23 meters, L2 is equals to 2.59 meters, and the DS is equals to 1 meter, where Cu1 is equals to 50 kilonewton per meter squared and Cu2 is equals to 108.75 kilonewton per meter squared. Determine the net ultimate point bearing capacity, the ultimate skin resistance, and the working load QW, where the factor of safety is equals to 3. So first, we need to compute the area of the base, where AP is equals to pi d squared over 4, and when you substitute the diameter, we get the total of 0.79 mm squared. Then, substitute to calculate the QP net using equation 13.33, where QP net is equals to AP times Cu times NC, where AP times Cu2 times NC. And when you substitute the values, we get the total of 768.71 kilonewton. Then, solve the ultimate skin resistance using equation 13.37, where the alpha is equals to 0.40 and the P is equals to pi times ds, where we get the 3.14 meters. And the QS is equals to summation of alpha times Cu times P times the change of length. And when you substitute those values, we get the total of 871.05 kilonewton. Next, divide the sum of QP net and QS by the factor of safety to determine the working load, where the QW is equals to QP net plus QS over factor of safety. And when you substitute those values, we get the total of 546.59 kilonewton. So here in problem 13.6, a drilled shaft in a cohesive soil is shown in 13.18 figure. Use Rees and O'Neill's method discussed in section 13.10 to determine the following. First is the ultimate load carrying capacity and the load carrying capacity for an allowable settlement of 12 millimeters. Given that Cu is equals to 145 kilonewton per meter squared and Cu1 is equals to 40 kilonewton per meter squared and Cu2 is equals to 60 kilonewton per meter squared, the ds is 0.76 meter and the dB is equals to 1.2 meter and the L1 is 6 meter, L2 1.5 meter, L3 is 3 meter. Also, the L4 is 3 meter. So part A for solving, first, we need to solve for the unit skin friction resistance using equation 13.40, where alpha times I is 0.55, and the change length 1 is equals to L4 minus L2, where we have 1.5 meter, and the change of length L2 is equals to quantity of L1 minus L4, close parenthesis, minus the ds, where we get the 2.24 meter. So in this formula, summation of Fi times P times change of length Li is equals to summation of alpha I times Cui times P times change of length Li. We have the 255.28 kilonewton. And from the equation 13.41, determine the point load per unit area, where QP is equals to 6 CUB times the quantity of 1 plus 0.2 times the L over dB, where we get the 1957.50 kilonewton per square meter. To check, the 9 Cu should be less than the QP, and our 9 Cu is 1305 kilonewton per meter squared. Since the 9 times Cu is less than the QP, so we need to use the 1305 kilonewton per meter squared. And then we need to compute the area of the base. AP is equals to pi dB squared over 4, which has 1.13. And then QP times AP is equals to 1475.92 kilonewton. Then, we need to substitute to calculate the ultimate bearing capacity. Qult is equals to summation of alpha I times CUI times P times change of length I plus QP AP, which has 1731.20 kilonewton. And then, we need to solve for normalized settlement, where we have to divide the allowable settlement over the ds, which has 1.58%, and then also the allowable settlement divided by the dB, which has 1%. Then, we need to calculate the side load and base load, where the normalized side load is 0.90, and the side load is 229.75 kilonewton. In table 13.16, the normalized end bearing is 0.572, and the base load is 844.23 kilonewton. Then, we need to combine side load and base load to calculate the total load. Normalized side load plus base load is equals to 1073.98 kilonewton. So in settlement of drilled shafts at working load, Vesic from 1977 proposed a method that separates the total settlement into 3 elastic components, which are elastic shortening of the pile or SE1, settlement of the pile due to the working load or QWP at the point load or SE2, and settlement of the pile due to the working load QWS along the pile shaft. The total elastic settlement of the pile head under the working load of QW is given by SE is equals to SE1 plus SE2 plus SE3, where SE1 is equals to quantity of QWP plus epsilon QWS times length all over AP times EP, where QWP is equals to working load at the pile point and QWS is the working load along the pile shaft. AP is cross-sectional area of the pile point, L is pile length, and EP modulus of elasticity of the pile material, and the epsilon is the correction factor. So for the point load settlement of a pile caused by the load carried at the pile point may be expressed in the form SE sub 2 is equals minor QWP times D over ES times the quantity of 1 minus mu S squared times the IWP, where the D is the width or diameter of the shaft, or minor QWP is the point load per unit area at the pile point, and ES is the modulus of elasticity of soil at the below the pile point, while the mu S is the Poisson's ratio of the soil and IWP is the influence factor. It should be less than 0.85. So in the shaft load settlement of a pile caused by the load carried at the pile point may be expressed in the form SE3 is equals to QWP times D all over ES times the quantity of 1 minus mu S squared times the IWP, where the IWP is equals to 2 plus 0.35 square root of L over D, where the P is perimeter of the pile and L is embedded length of the pile, while the IWP is the influence factor. So here in this problem, given that L1 is 8 meters, L2 is 3 meters, DS is 1.5 meters, CU1 is 50 kilonewton per meter squared, CU2 is 105 kilonewton per meter squared, and working load QW is 1005 kilonewton. Estimate the elastic settlement at the working load. Use equations 12.88, 12.90, and 12.91. Take the epsilon is equals to 0.65, EP is 21 times 10 to the 6 kilonewton per meter squared, ES is 14,000 kilonewton per meter squared, and mu S is 0.3, and QWP is 250 kilonewton. So first, we need to solve for the elastic shortening of the pile using equation 12.88, where the QWS is equals to QW minus QWP, which we have 755 kilonewton, where the AP is just equals to pi over 4 times ds squared, which we have 1.77 meters squared. In the SE1 is equals to quantity of QWP plus epsilon QWS times the L all over AP times EP. And when you substitute those values, we get the 0.00022 m or 0.22 millimeters. Next, compute the settlement due to the working load at the pile tip using the equation 12.90. Since the CP in table 12.14 is stiff clay, we will use the value of 0.04. And QWP is equals to QU sub B times NC, which we have the result of 945 kilonewton per meter squared. And SE sub 2 is equals to QWP times CP all over DB times QP, which we will have the value of 0.0071 m or 7.1 millimeter. And then you will determine the settlement due to the working load along the pile shaft using equation 12.91 and equation 12.92, where the IWS is equals to 2 plus 0.35 square root of L all over DS, which we will have the result of 2.91. And in the SE sub 3 is equals to quantity of QWS all over P times L times quantity of DS all over ES times the quantity of 1 minus mu S squared times the IWS, which we will have the result of 0.0042 m or 4.2 millimeters. Then you will substitute to solve for the total settlement using the equation 12.87, where we will sum up all the results of SE sub 1 plus SE sub 2 plus SE sub 3. Then we will get the SE of 11.46 mm.
Lateral load, carrying capacity, characteristic load, and moment method. The characteristic load and moment method, developed by Duncan et al. In 1994, is a simplified approach for estimating the lateral load capacity of drill shaft by defining two reference parameters, the characteristic load QC and characteristic moment MC. These parameters are used to normalize applied lateral loads and moment into dimensionless ratio, which is Q over QC and M over MC, which are then correlated with shaft deflection, rotation, and bending behavior. Using empirical relationship, this method reduces complex soil structure interaction into generalized design curve, making it an efficient tool for preliminary analysis. Characteristic load for clay. QC is equals to 7.34 dA squared, open parenthesis, EP times RI, close parenthesis, times, open parenthesis, CU over EP times RI, close parenthesis, to the power of 0.68. Characteristic load for sand. QC is equals to 1.57 dA squared, open parenthesis, EP times RI, close parenthesis, times, open parenthesis, gamma prime times DS times P prime times RP over EP times RI, close parenthesis, to the power of 0.57, where DS, diameter of drill shaft, EP, modulus of elasticity of drill shaft, RI, ratio of moment of inertia of drill shaft, section to moment of inertia of a solid section. Note, Ri is equals to 1 for uncracked shaft without central void. Gamma prime, effective unit weight of sand. P prime, effective soil friction angle. Rp, Rankine passive pressure coefficient is equals to tan squared, open parenthesis, 45 plus P prime over 2, close parenthesis. The graph shows the relationship between QS over QC and MS over MC with XS over DC. As XS over DC increases, both ratio increase. The fixed head condition gives a higher discharge compared to the free head condition. Momentum ratio is also increases but at a lower rate than the discharge ratio. Deflection due to load applied above the ground line. If a load QG and a moment mg are applied at the ground line, the maximum moment in the drill shaft can be determined in the following manner. Step 1. Compute the combined deflection. It combines effect of both shear force QG and moment mg. Step 2. Solve for characteristic length T. XO is equals to 2.43 times QG over EP times IP times T cubed plus 1.62 mg over EP times IP times T squared. Step 3. Compute bending moment at depth. Mz is equals to AM times QG times T plus BM times mg. EM and BM are dimensionless moment coefficient. Sample problem. A free-headed drill shaft in the clay is shown. Determine the ground line deflection, the maximum bending moment in the drill shaft, the maximum tensile stress in the shaft, the minimum penetration of the shaft needed for this analysis. We're given DS 1 meter, CU 100 kN over m squared, RI is 1, EP is 22 times 10 to the power of 6 kN over m squared, QG 150 kN, mg 200 kNm. Also, we need to compute the moment of inertia of a circular shaft section. IP is equals to pi d to the power of 4 over 64. Step 1. Compute for the characteristic load of clay. QC is equals to 7.34 ds squared times, open parenthesis, EP times RI, close parenthesis, times, open parenthesis, CU over EP times RI, close parenthesis, to the power of 0.68. Step 2. Compute for the characteristic moment of clay. MC is equals to 3.86 ds cubed times open parenthesis EP times RI close parenthesis times open parenthesis CU over EP times RI close parenthesis to the power of 0.46. Step 3. We need to solve the load ratio. QG is over QC. Step 4. Calculate the moment ratio. MG over MC. Step 5. Compute XOM over DS. Step 6. Compute XOQ over DS. Step 7. Compute QG over QC plus QGM over QC. Step 8. Compute MG over MC plus MGQ over MC. Step 9. Compute XOMQ. Step 10. Compute the combined deflection XO is equals to 0.5 times XOQM plus XOMQ close parenthesis. Part B. The maximum bending moment in the drill shaft. Step 1. Solve for characteristic length. XO is equals to 2.43 times QG over EP times IP times TQ plus 1.62 times MG over EP times IP times T squared. Calculate the moment in the shaft at a dip below the ground surface. MZ is equals to AM times QG times T plus BM times MG. Part C. Calculate for the maximum tensile stress in the shaft. Sigma is equals to M max open parenthesis DS over 2 close parenthesis over IP. Part D. Determine the maximum penetration of the shaft needed for the analysis. EP times RI over CU. Drill shaft extending into rock. Zhang and Einstein 1988 analyzed a database of 39 full-scale drill shaft tests in which shaft bases were cast on or in generally soft rock with some degree of jointing. Based on these results, they proposed QU net is equals to QP plus QS is equals to QP times EP plus FP times L, where end bearing capacity QP can be expressed as QP times EP is equals to open bracket 4.83 open parenthesis QU times M times N over M squared close parenthesis to the power of 0.51 close bracket times open bracket EP times M squared close bracket. Also, the side resistance QS for smooth socket is FP times L is equals to open bracket 0.4 open parenthesis QU times M times N over M squared close parenthesis to the power of 0.5 close bracket times open bracket pi times ds times M close bracket times open bracket L times M close bracket, and the side resistance QS for rough socket. FP times L is equals to open bracket 0.8 open parenthesis QU times M times N over M squared close parenthesis to the power of 0.5 close bracket times open bracket pi times ds times M close bracket times open bracket L times M close bracket. Sample problem number 1. Consider the case of drill shaft extending into rock as shown in. Let L 4.5 meter, L1 3 meter, DS 0.9 meter, QU rock 72,450 kN over M squared. QU concrete 20,700 kN over M squared. EC 20.7 times 10 to the power of 6 kN over M squared. RQD rock 80%, ECO rock 2.48 times 10 to the power of kN over M squared. CS 457 mm and sigma 3.81 mm. Estimate the allowable load-bearing capacity of the drill shaft. Use a factor of safety 3. Step 1. Calculate the ultimate unit site resistance. F is equals to 6.564 times QU to the power of 0.5. F is equals to 0.15 times QU. Step 2. Calculate the ultimate capacity based on the site's resistance only. QU is equals to pi times ds times L times F. Step 3. Calculate the settlement of the shaft at the top of the rock socket. E mass over E core. E mass is equals to 0.468 times E core. EC divided by E mass L divided by ds. Compute the EC. EC is equals to pi times ds squared over 4. Compute SE is equals to QU times L over EC times EC plus EQ times IF over ds times E mass. Step 4. Calculate the maximum load that the drill shaft can safely carry. Q all is equals to QM over Fs. Sample problem number 2. A drill shaft extending into a shale formation for the intact rock course given QU 4.2 mn over m squared. Estimate the allowable load-bearing capacity of the drill shaft. Use a factor of safety 3. Assume a smooth socket for site resistance. We're given QU 4.2 mn over m squared, Fs 3, ds 1 meter, L1 3 meter, L2 4 meter, and length 7 meter. Step 1. Calculate the in-bearing capacity. EP is equals to pi times d squared over 4. Compute the QP is equals to EP open parenthesis 4.83 times QU to the power of 0.51 close parenthesis. Step 2. Calculate the side resistance. QS is equals to 0.4 times QU to the power of 0.5 times pi times ds times L. Step 3. Calculate the maximum load that the drill shaft can safely carry. Q all is equals to QU over Fs is equals to QP plus QS over Fs. Summary: drill shaft are deep foundation made by excavating holes and filling them with reinforced concrete. The chapter covered their types, construction methods, load transfer mechanism, and ways to determine load capacity in sand and clay. Based on bearing capacity or settlement, it also discussed lateral load capacity and shaft in rock. That's all our report. Thank you.